Okay, now I am on YouTube. I don't think it's easier to see in that way, is it? I need to find a way this time for this autofocus. Yeah, I will write with black. Hopefully everything will be visible. Okay, so let us start the lesson today. As you see, I have written primitive functions. I think I will skip section 2 in this chapter. I want to go to the notion of the primitive functions first, and then I will come back and cover that part. I think after studying the derivative is more or less finalized into a desired point, I think it's very natural to go to the primitive function discussion because it is the inverse operation, or a reverse operation of differentiation, yes? So when you differentiate, yeah, this will make us trouble, I think, today again. So I will try not to move back and forth. Might be this is sensitive to this one. Yeah, I will try to find a way out of this autofocus thing. It should be very simple, but I don't know why it makes it so complicated. Anyway, so today we want to talk about the notion of a primitive function. As I told you here, if you have a function x to the 3, for example, differentiation will take you from x to the 3 to a new function, 3x squared. This is differentiation. And then anti-differentiation will take you in the reverse direction. Okay, so here, this is the function, this is its derivative. Now, this function, so this function here is called the derivative of this function. This function here is called a primitive function of this function here. Yes? Is that visible? Exactly, I don't know what's happening here today with this camera. Yeah, please confirm that somehow you can see it. Can't you? Can you? Yes. Okay, thank you. So, you see here, I say that this is the derivative of this function, but I am saying that this is a primitive function of that function. Yes, because there are different functions whose derivatives are equal to this. For example, if I have x to the power of 3, derivative is 3x squared. But even if I have x to the 3 plus a constant 1, this is of course a different function, but its derivative is still 3x squared. So I can ask about the derivative, but I should ask about a primitive function in general, because there are different functions with that property. But they are not radically different. As I will talk a little bit about that, they cannot differ a lot, okay? They can differ at most by a constant. So that is also a crucial point. I will come back to it. Anyway, so this is called the function let me consider now this to be my function. This function is a primitive function, and the symbol we use, this is the standard notation, we denote it by the capital letter of this letter, okay? So I would say that this is a primitive function of that one. So now let me give you the formal definition. So definition. A function capital F is said to be a primitive function of the function f f. In principle, I add something on an interval I. Here, at the level of your lesson, you don't need to emphasize on this part, but that is the real definition of that. A function of the function f on an interval I if the derivative of f, the derivative of the capital F is equal to the small f. And of course, if I want to define it precisely, I should say for all, this means for all x in the interval. But you don't need to be worried about what I have written in the pair of brackets. We only talk about functions that are differentiable on whole range or a very big interval and an unbounded interval. So you don't need to be worried about that. So anyway, if I want to make it simple, the capital F is called a primitive function for the lowercase letter f if the derivative of the capital one is equal to the derivative, is equal to this function itself. Okay, so let me give you example. So functions f, let me say f1 of x equals to sine x, and f2 of x equals to sine x minus 5, for example, are both primitive functions of the function little f of x equals to cosine x. Since, why this is true? Since if I take the derivative of the first one, the derivative of sine becomes cosine x, and that is equal to the function f of x. And if I take the derivative of the second one, that constant doesn't make any problem for me. The derivative of this function is still cosine x, and cosine x is again the little function f of x. So as simple as that. So the reason that I call these two functions primitive functions of cosine function is because when I take the derivative of these two functions, it becomes the cosine function. So that is just the definition of the primitive function. Okay. Yes? Yeah? What? Am I making mistake? No. The derivative of sine is cosine. So you see, the capital F. Yeah. So I was a little bit confused myself, but I have done it correctly. Because the derivative of the capital F should be the small f. So what I have written is correct. Yeah, thank you anyway. Okay, so let me also increase the volume on my computer because I was not able to hear you properly. Okay, now in your book, they haven't used any symbol for primitive functions. In principle, the symbol for a primitive function is called the indefinite integral. Indefinite integral. I want to avoid that because it is not in the book. But the symbol is like this, exactly like the integral. But in the integral, you have a lower bound and an upper bound on top of these. But an indefinite integral, you don't need to write that. So for example, if I want to write this, I would write that the primitive function of cosine is equal to sine of x. Okay? And then probably the reason that they don't want to use this symbol, because then you have to, for some reason that becomes clear in the university, for example, you need to write something of d of x here. To avoid this ambiguity, they have avoided that. So, but in that language, I can say that the primitive function of cosine, saying that the indefinite integral of cosine is sine, because when I take the derivative of this function, it becomes that. But this is not the only function. Any function of this form plus a constant is also a primitive function. So when you see this, it means that write all of them in front. But let me just stick to the notations in the book. So let me just invent something for myself, because we need to have a symbol for mentioning, to denote a primitive function. So let me just, I don't know, write PR for primitive. Okay? I want to use this symbol. I will not use it that much, but I want to write something that I have to have a symbol for that. And let me avoid this, okay? Okay, so let me write a remark here. If capital F is a primitive function of little f, then if capital F plus a constant for any constant c is also a primitive function of little f. This is something at the level of your lesson, you can confirm that. Let us do that, of course, together. What I am claiming that if I give you a primitive function for this function, little f, then you have infinitely many of them available suddenly. You just need to add any constant that you like to the primitive function that I gave to you, and then you will still have a primitive function. Okay? This is very easy to confirm, but the reason that I am writing it as a remark, because the other way around is also true, even though you don't have enough mathematical machinery at your disposal to be able to show it rigorously, but I want you to know it as an extra piece of information, okay? So let me first of all confirm this. Okay, you are telling me that f is a primitive function, so let me write a PR, a primitive function of f. What does this mean? this means that the derivative of capital F is a small f. Now I want to show that this new function is also a primitive function. It's very simple. What I need to do, I need to take the derivative of this new function. According to the sum rule for derivatives, it becomes the derivative of the first one plus the derivative of the second one. But the derivative of this first one is little f. The derivative of the constant is 0, so what I get is f. So as simple as that. So because the derivative of this function is this function, it means that this is also a primitive function. So it's very easy to, at the level of your lesson, to understand that. But the problem is that the remark is somehow the other way around. This I want to emphasize. Moreover, if f1 and f2 are primitive functions of the same function, then this is not trivial. Then they differ at most by an additive constant, which is not trivial at all. If I imagine two functions, of course, if you want to think about, you are simplifying it in your brain, but assume that in the bag of all possible functions, even if those functions that you don't know anything about, I am claiming that if two functions are primitive functions of the same function, they cannot differ tremendously. At most, they can differ by an additive constant. So that's a huge claim, actually. So moreover, if f1 and f2 are primitive functions of the same function, then the difference between them is a constant. Okay? So then f1 minus f2, or the other way around, is a constant. So if I want to write it as a formula type way, so you would say that, okay, if you tell me that when I take the derivative of capital F1, it becomes little f, and if you tell me the derivative of this one is also little f, I can immediately conclude that f1 minus f2 is a constant. Or it can be formulated in a different way. When you say the derivative of this is equal to f, the derivative of this is also equal to f. So it means that if someone tells me that the derivative of f prime 1 is equal to the derivative of this one, I cannot conclude that these two functions are the same. What I can conclude is that f1 minus 2 is a constant. Or in other words, if someone tells me that the derivative of a function is equal to 0, there is no other choice. Yes, be careful that this means that the derivative f of x is a constant. You might think this is trivial. It is not. What you know is that if a function is constant, its derivative is 0. But is it guaranteed that if a complicated function, is it possible that I have a super complicated function, I take the derivative of that function, and a lot of things goes on, and a lot of things go on, and then sometimes they simplify each other, and it becomes 0 without the function being a constant? It turns out the answer is no, but it is not trivial. I want you to understand. What is trivial is going from this direction to that direction, not the other way around. But it turns out that both of them are correct. This blue arrow one is at the level of your lesson. Going in this direction is not at the level to understand exactly. This is not complicated. You immediately understand it when you go to the university. It's a very simple one, but it is not at the level of your lesson. I want you to know that this is the correct one. And you might think that, can this idea be somehow powerful? Okay? Let me try to show that to you. Let me give you an example here. I wrote some examples here if I have them with me. Yes. Let me give you an example to make this idea clear. Let me give you three functions. A function f of x, f1 of x is equal to sine squared x. Another function f2 of x, let me give it as minus cosine squared x. And let me tell you this function, f3 of x is equal to minus 1 over 2 cosine 2x. Okay, let us be patient a little bit and differentiate these functions. First of all, how much do you think these functions are differing from each other? Yes. So it seems that might be they are not. They seem completely different. Yes. Of course, if you have trigonometry in your head right now, you see that they are not that different. But let us check. First of all, might be there is no easy way to understand you. They have a relation. There is a nice and simple relation between these. Between these, you already know might be. Okay, but let us check. Let me take the derivative of the first one and see what is the answer. If I take the derivative of the first one, I hope that you remember, this is the chain rule. So 2 goes down, it becomes 2 sine x. But I have to multiply by u prime, which is cosine x. So this is the derivative. The derivative of the first one is what is written on the board. And let us do the derivative of this one. So the derivative of this one, what happens? 2 goes down, it becomes minus 2 cosine x. But because of the chain rule, I have to multiply by the derivative of cosine, which is minus sine. But if I multiply this minus sign by that minus sign, it becomes 2 cosine x sine x. Which one? This one is exactly that one. Yes? And then let me take the derivative of this function. F prime of 3x. Again, this is a chain rule. Minus a half is there. The derivative of cosine 2x is negative sine 2x, but multiplied because of the chain rule by the derivative of this angle, which is 2. But then let me simplify. This minus sign and that minus sign go away. This 2 will cancel that 2, and I will have sine 2x. But if you remember trigonometry in chapter 2, using the double angle formula for sine, this becomes 2 sine x cosine x. So what is happening now? The derivative of all these three functions are the same. So this definitely means something. Even though they look completely different functions, but this calculation confirms that the derivative of all of them is equal to the same function. According to this moreover part here, it means that the difference of any of these two functions is a constant. Doesn't depend on the value of x. And we can confirm that. Let us calculate the difference f1 and f2, of f1 and f2. So what is f1 of x minus f2 of x? f1 of x is sine squared, minus f2 of x is minus cosine squared of x. Then what happens? It becomes sine squared x plus cosine squared x. But is this a constant? Yes, because sine squared x plus cosine squared x, independent of the choice for x, is equal to 1. So you see, I'm not proving this, but I'm giving you some motivations. I started with three functions. They look somehow a little bit different, But calculation confirms that all of them are the derivatives of the same function. So if this is going to be true, I can immediately say that, okay, so these functions should differ only by a constant, which might not be very transparent here. Let me check the other one. Let me check the difference between this one and that one. So what is f1 minus f3? What is f1 minus f3? So this means that f1 is sine squared x minus f3. Minus minus becomes positive. Okay, but is this a constant? What I'm saying to you is that if you know this theorem, you should be 100% sure that this is a constant, even though it is not that simple to see. It is a constant. It was so famous that I was able to write 1 in front of it, but this is not a famous one. But if this theorem is correct, then I have to be sure that this is definitely a constant. Do you know how can I see that this is a constant? Do you know what is the meaning of a constant? Why this is called a constant? It means that it doesn't matter what value for x I choose. I have infinitely many choices for x, but whatever I choose, calculate this one and calculate this one, independent of the value for x chosen, the answer is 1. This is the meaning of being a constant. So I am claiming the same thing here. I am claiming that if I choose any value for x, I add them, and I calculate this, it becomes a constant. If I change the value of x, the value at the constant does not change. That is what I mean. Okay, do you see how can I confirm that this is a constant? It needs some formulas, of course. You might have it in your memory. This is the cosine of double angle formula, yes? So I can write it as sine squared. I just write it, I have it in my memory. If you remember, there were 3 formulas when it comes to cosine 2x, but I use one of them, which is useful in this problem, and that is 1 minus 2 sine squared x. So what I have written, instead of this, I wrote this. And then what happens, I multiply the negatives, the 1/2 inside, so it becomes sine squared x plus 1/2, and minus 1/2, 1/2 minus 2 becomes minus 1 minus sine squared. So you see, it's nice. This is gone, so my prediction was correct. Even though it was not clear from the beginning that this is equal to a constant, but I trusted the theorem, and I confirmed that yes, even though it was not clear what that value is, I calculated and I got a constant independent of my choice for x. You can do this as an exercise for yourself. You can calculate the difference between these two, and definitely if you use another formula for the double angle formula for cosine, you will get that is also a constant. Is that clear? So it was actually a simple problem, but a nice problem. So it means that if I give you this function in the exam, for example, and I ask you find a primitive function for this function, might be you give this answer to me. Some of you might be able to get this, or some of you might be able to get this. It depends. Might be you are using different calculation methods. One of you are getting this, one of you are getting this, one of you is getting this, but this is completely correct. All of these answers are correct. And by the way, we confirm that they don't change, they don't differ radically, they differ only by a constant. Okay? Now let me, for example, sometimes this idea is very useful if you want to prove some of these theorems. For example, so one of the consequences of this is if the derivative is 0, don't worry about that. The function is a constant. That's a consequence, actually, of that. For example, I was trying to think a lot for finding a nice formula, but I think the easiest one is this one. You already know that this is not a big surprise for you, but I couldn't find any kind of examples at the level of high school math. Might be there are, I can probably investigate a little bit more. But let me write this example. Show that sine squared x plus cosine squared x is equal to 1. Okay? Of course, you already know that. This is a very famous identity. We use trigonometric methods to prove this. But assume that you have a complicated formula. So if you want to show that something depending on x is equal to a constant, this trick might work. And it is somehow a very nice trick. What we do, we say that of course, I want to use this theorem to prove that. I would say for example, take this function. Let capital F be equal to f of x be equal to sine squared x plus cosine squared x negative 1. You might be, okay, you might ask yourself why I am doing this. You need to be patient to see that what will have this for us at the end. Let this be equal to this. I don't want to use any trigonometry, of course, here. Then I calculate the derivative. Then what happens if I calculate the derivative? The derivative of this one, 2 goes down, it becomes 2 sine x, but the derivative of sine becomes cosine. And the derivative of cosine squared, 2 goes down, it becomes cosine, but I have to multiply by the derivative of cosine, which becomes negative sine, minus the derivative of 1 is 0. But what is the derivative now? You see, this is 2 sine x cosine x. And 2 times minus 1 is minus 2 sine x cosine x. And then what is the answer? The answer is 0. So what I got, so it means that if I define my function in this way, I was successful to show that the derivative of this function is 0. But if you trust on this theorem, if you take that theorem for granted, so if the derivative of a function is 0, what can I conclude? I can conclude the function is a constant, where c is a constant. Yes, so I can conclude that f of x is equal to a constant. So what does it mean? It means that I showed that this function is a constant c. So therefore, sine squared x plus cosine squared x minus 1 is equal to c. And then I move 1 to the right-hand side. It means that sine squared x plus cosine squared x. Let me stop here. How can I find the constant? Can you tell me? What I have shown so far is that this expression is a constant. But which value? What is the value of this constant? How can I find that value? Of course, if I don't find that value, I move 1 to the right-hand side. It becomes 1 plus c. That might be 1, that might be 2, because I don't know c, so because it becomes 1 plus c. If c is 0, the answer is 1. If c is 1, the answer is 2. If c is negative 3, the answer is negative 2, for example. But how can I really fine-tune exactly what the value of c is? You can think about it until I am just erasing the board. Yes? Yes? Can you hear me?
Isn't sin squared plus cos squared always 1? So 1 minus.
No, that the problem is that I want to show that, yes? I want to teach you this new trick. Of course, I know that this is equal to 1. So why I'm asking you show that? When I say show that, it means that using this new method, not trigonometry, I want to use derivative showing that this is valid. So might be you are confused. Of course, we know that sine squared plus cosine squared is equal to 1. If I ask you why, how do you answer that? You can answer me in the way that I taught you when I was teaching trigonometry, using the notion of the unit circle. So it needs trigonometry. If you use trigonometry, you are okay, you will get this identity. But now I'm telling you that assume that you don't know trigonometry, you want to show this using the notion of derivative and primitive functions. Is the question not clear? Yes?
Where did you get minus 1 from? Like the primitive?
No, so now listen to me. Listen to me. No, listen to me. Yeah, listen to me because I told you that you need to be patient, wait until the end of the problem to see what I am presenting you. Okay? You cannot understand why I have written minus 1 there unless you see the full problem in its generality, and then might be you can use this trick for another problem. Yes? What I am trying to tell you, just trust me and come with me. Okay? Forget about this for the time being. I am telling you that let us f of x be this. Okay? And I take the derivative of this function using the knowledge of the derivative I have, the derivative becomes 0. So this capital F, if I ask you what is the derivative of the capital F, you say that this capital F derivative is 0. And if I ask you then what can you conclude about that? You say that if the derivative is equal to 0, you told me to trust you on that. It means the function is a constant. But what is the function? I myself defined it in this way. Why? You need to wait and see. It is not clear yet. But at least it becomes clear that this expression here is equal to a constant. So it means that I was able to show this is correct. I just want to wait again. Do you understand my words so far? I haven't drawn any conclusion yet. I'm waiting for you if you have any questions.
Yes.
Okay. Now we want to find this C. If you cannot find this C...
When I talk, it takes a little bit of time to reach you.
Yeah, I understand. No problem. No problem. I wait for you. Okay? So this is equal to C.
I just wanted to say that when we talk, it takes time to reach you.
Yeah, I understand. I understand. I will wait for you. I understand that. Thank you. So sine squared x plus cosine squared x minus 1 is equal to C. So what I showed that sine squared x plus cosine squared x is minus 1 is a constant. So this is something very important. I confirm, actually I was able to show that this expression on the left is a constant. It does not depend on which value I am choosing for x. It is always a constant. But how can I find that constant? Can you tell me now?
Maybe we can calculate the function at some value of x.
Very, very good. Thank you. That's the one. So for example, if I ask you, I have a function, f of x is a constant. Forget about this momentarily. I say that I have imagined a function in my head. I don't tell that function to you, but I tell you that that function is a constant. And I give you one extra piece of information. I tell you that f of minus 2 is 7. So I tell you that I have a function. I guarantee the function in my head is a constant function. I provide you another extra piece of information. I tell you f of minus 2 is 7. What can you conclude about C? C is 7. That's it. Exactly. So what I have done here, I have confirmed that this combination is a constant, which was not trivial at all. If you don't know trigonometry, how should we know that this is a constant? Because it depends on x, apparently. But this calculation confirms that no, there is no x dependence. This is apparent x. This is just a fake independence. In principle, this combination is a constant. Now I want to find the constant. So I have to calculate this value for a constant, for a particular value of x. For example, let us choose x equal to 0, or x equal to 90 degrees, or whatever I know how to calculate it. If I put 0 here, it becomes sine squared 0 plus cosine squared 0 minus 1 is equal to this constant c. But sine of 0 is 0, it is 0. Cosine of 0 is 1, and this is 1, so it is equal to c. So it means that c is equal to 0. When c is equal to 0, I put it back here. What I get sine squared x plus cosine squared x minus 1 is equal to 0. And then I move 1 to the right-hand side. It becomes 1. And this is a proof, another proof without using trigonometry at all. Yes? So if you don't understand exactly what is going on, that's not a big deal, even though from my point of view, it's not a very complicated thing. So I defined a function for myself, and I took the derivative of this function, and I was lucky, the derivative becomes 0. I concluded that the function is a constant. So this means that f of x, I replace this for f, this is this, and equal to c. This is also a good progress, because who knows, if you don't know anything about trigonometry, put yourself in that position. If you don't know anything about trigonometry, how do you know that this expression is a constant independent of value of x? So that's a tremendous progress. We realize that this combination is a constant. So this means, now I want to find that constant. When you tell me that this is a constant, regardless of the value of x that I put in, so it means that I can put 0, any number there, the value that. So I put 0 here, and I calculated c is equal to 0, and I put this back, and I moved 1 to the right-hand side, then I have my operator, then I have my identity. Okay, but if you don't understand this, that's quite okay for me. Don't worry about that. But I think you need to know the constant. If the derivative is 0, the function is constant. This is not trivial, even though the other way around is trivial. If the function is constant, its derivative is equal to 0. Okay. Now let me start what I want to talk. Again, there is a mixture of Math 3C and Math 4, but yeah, let us combine them into a little bit harder problems. Most of this part you have already studied in Math 3C, but as usual, I don't consider that knowledge for you from your Math 3C course. Okay, something that is very important, I don't know why they haven't written down in the books, in your books, is this. If I ask you, so primitive function, let me use PR for primitive function. Primitive function of f plus g is equal to the primitive function of f plus primitive function of g. This is comparable to this rule of differentiation. Okay. So let me write capitals here for you so that you are not confused. Do you remember we had a rule? If I have two functions, I want to take the derivative of the sum. It becomes the derivative of the first one, the derivative of the second one. Analogous to this is this rule. If I want to find the primitive function of the sum of two functions, it becomes the primitive function of the first one plus the primitive function of the second one, comparable to this. Actually, this is a consequence of this theorem. And then there was another theorem, if you remember. If I have a constant number multiplied by a function and I want to take the derivative, do you remember? I didn't care about the constant, I just write it there, and not just to take the derivative of that function and then multiply it. Similar to that rule is this. If I want to find the primitive function of a constant multiplied by a function, I can pull the constant out and just focus on calculating the primitive function of f. Okay, but unfortunately, the analogy stops here because we learned that there is another rule, a product rule. This is f prime g plus fg prime. It is not easy at all to translate something here. You will study a little bit about that, not a little bit, quite extensively about this rule, translation it into the primitive function. That is called integration by parts. But for the time being, we don't know. This is a question mark for you. And even for the quotient rule, we don't know. Okay? So what I want to tell you that these two rules for derivatives translate themselves to these new rules for primitive functions. Okay? Let us try to prove one of them. Let us check why this is true. Okay, so let a primitive function of f be capital F and primitive function of g be capital G. Okay, so what is the translation of this? When you say that the primitive function of little f is capital F, it means the derivative of the capital F is equal to the little f. And when you say that the primitive function of little g is the capital G, it means that the derivative of the capital G is little g. This is the meaning of being a primitive function. Okay, now let me add these two expressions side by side. This becomes capital F prime plus capital G prime, and then this becomes equal to F plus G. But according to this rule of derivatives, instead of F prime plus G prime, I can write F plus G prime. And on the right-hand side, I have F plus G. Okay, what can I conclude from here? I have a function. When I take the derivative of that function, it becomes this function. So this means that this function is a primitive function for this function. So this means that f plus g is equal to primitive function for f plus g. Let me repeat this part. Primitive function of f, let us call it f. This means this. The same for this. I add these two relations side by side. And then I use this rule from derivatives to collect this into this form, and I want to translate this again into this new language. I have a function, forget about the name of the function. The derivative of this function is equal to that function. So this means that what I have here is a primitive function for this one. So it means f plus g capital is equal to the primitive function of f plus g. But what was f? F was primitive function for f. What was g? G was primitive function for g. This becomes primitive function of f plus g, and that is exactly what I wanted to show. And this is also a very simple exercise. You can do that. We always use them. I don't know. In the book, they haven't talked about this at all, even in Math 3C, Math 4, but they are using it all the time. The same for primitive functions. So you need to know about these things. And the same is true if I take it negative. If I make it negative. And the reason is that this formula is also valid when this is a negative sign there. Okay? Now let me ask you to test your understanding a little bit here before continuing.
Mr. Boba,
Yes?
in very formal mathematics, is there a way to say that a plus minus sign is the same as another plus minus sign? That is to say, they are symmetrically linked pairs.
I don't exactly understand the question.
Well, because the equation only holds if the one of the plus minus signs is the same as the other one.
No, this means that this is convention. If I want to write it in this way, by convention, it means that when you read the upper sign, continue reading upper sign all the time. And when you read the lower sign, continue to read the lower sign all the time. Yes, exactly, because otherwise there would be 4 possibilities. Yes, this is the convention. Yeah, that's exactly the case. Okay, let me ask you one question. Can you answer this question for me? What is a primitive function for f prime? Let me repeat. What we say, when we say primitive function of a function, I am asking you, give me a function whose derivative is equal to what is inside. So when I ask you what is the primitive function of f prime, I am asking you, give me a function whose derivative is this, exactly, is equal to f. Is that understandable for everyone? What is a primitive function for f prime? It means that give me a function whose derivative is this function. But it is clear, if I give you f, you take the derivative, it becomes f prime, I am done. But of course, f is not the only answer. F plus 2 is also a correct answer. So you can write f plus c. Any constant. Okay, let me ask you again. What is this one? I am asking you, give me a function whose derivative is f double prime.
F prime plus c.
F prime plus c, exactly. So you see that these two operations are more or less opposite, except for this x degree of freedom c. If you ignore that, if I give you the function, you differentiate, go to f prime. Now, if I primitive function this, you go back to this function. If I give you f prime, you take another derivative, you get f double prime. It is clear when I take the primitive function, you go one level back. If I want to go from f double prime to f, I have to do the primitive function twice. From f double prime to f prime, and then from f prime to f. So these are important concepts that I want you to understand. Okay, yes?
Couldn't c be assumed to be 0 if we already know the function f?
No. Usually, I want to talk about that. Usually, in the book, they ask you find all primitive functions. Sometimes they say a primitive function. Sometimes they say the primitive function. Now, I want you to know about that. When they say all primitive functions, it means that you need to show to the examiner that you know about this. You have to put this C there. So it means that you are showing to the examiner that I know about what is the meaning of all. But if I ask you about a primitive function, you can choose whatever you like for C. Of course, the easiest choice is 0. In that case, I don't put C there, because if someone asks me why you don't put C there, because I say that you want me 1, and I chose C equal to 0. This is why you don't see there. You don't see C there. And if they ask you the primitive function, they cannot ask you about the primitive function unless they provide you with an extra piece of information so that you can use that piece of information to exactly find the value of C. I will give all examples, but you can write it down somewhere to understand the differences. All means that putting C in your answer is necessary. A primitive means that you don't need to be worried about C at all. The primitive, it means that you have to put C in your intermediate answer, use an extra piece of information, which is definitely given in the problem, to find that C. Okay, so yeah, this is important to write it somewhere. We will talk about that. But let us, before going to this, let me start now. The main question is that, how can I do this reverse operation? So forget about many of these things momentarily. Just try, you want to answer this question. If I want to draw an analogy between derivatives, I gave you a function. Then from Math 3C until the end of this Math 4, you learned a lot of rules so that if I give you a function, even complicated functions, you can apply those rules and then you can find the derivative of the function. Now, more or less, we want to develop some of those ideas in the reverse direction. We want to cook up some rules so that if I give you a function, you can tell me the original function, the primitive function, the function that after differentiation becomes this function. The bad news is that this is not always possible in terms of elementary functions. This is the bad news. So it means that it is, if I just randomly, even if, by the way, it doesn't necessarily have to be a very complicated function. If I say you e to power x, if I ask you what is a primitive function for e to power x, I am asking you about a function whose derivative is equal to this. Everyone knows about that, hopefully, and that is e to power x, as simple as that. But if I just write e to power x squared, and I ask you the same question, it turns out that none of these functions, none of these elementary functions that we know so far is actually have this property whose derivative is this. So this is, first of all, I want you to understand that this is not easy. In principle, I can write any function and I ask you to differentiate it. But I cannot write any function and I ask you to find the primitive function or a primitive function. For this simple case, you see, it doesn't look complicated. If I ask you to differentiate this, it is a matter of seconds, yes? The chain rule, e to power x squared, the derivative of that, finished. This is the derivative. But if I ask what is a function whose derivative is equal to this, it is not among these elementary functions that you know. We can artifact a function whose derivative is equal to that. But that function is not among the functions that we know. So this is one thing you need to put in mind from the beginning. Okay, but the situation is not as bad as that. We have some tricks and techniques, and you will spend a quite long time in a calculus course in university to learn a lot of tricks and techniques to solve these problems, and they could be quite hard. But what we want to do here, exactly according to what we did for differentiation. Do you remember what was my strategy for differentiation? We had some general rule. This is one general rule. The other general rule was that three other general rules you studied this year: the product rule, the quotient rule, and the chain. Okay, for the level of your math, you have only two general rules for primitive functions. I have written them on the board. Even though they are not in the book, they are using it, so you need to know that. Okay, and then after that, what I did for derivatives, do you remember? I set up a table of famous functions. I put the functions on one column, and I put the derivative of the functions in front of that, in another column. I want to do the same thing for primitive functions. So it means that I want to complete a table similar to that and try to understand how to use this table effectively. Okay, so what I do, some main part of this lesson and probably next week would be to complete this table now again. So this is the reversed order. So let me just write little f, and then let me write capital F for the primitive function. Let me start with the simplest possible scenario. What is the simplest possible function? A constant function. Yes? So if I give you a constant, so if you don't mind, let me write the constant here, k. Constant. Okay, I am asking you, tell me a function whose derivative is equal to constant k. For example, if I give you 2 and I ask you, yes, exactly. If I give you 2 and I ask you, give me a function whose derivative is 2, it's very simple. So that's a guesswork here. It's 2x. If I give you 3, the answer is 3x. But of course, 3x and 2x are not all of them. I have to add a constant at the end, yes? So in principle, if I give you k, it becomes k times x, and then probably plus a constant. This is why I changed the name of constant to k, because I want to reserve c for this constant of integration or primitive function. Okay, so that's it. So if I ask you what is a primitive function for 1, it's x plus c, or you can say x. Let me write this by blue. These are the specific cases. If this constant is 0, then I put 0 here. This vanishes and c is left. If I give you this constant to be 1, then k is 1, so it becomes x plus c. This is only given in the formula sheet, but these are simple. You can immediately extract it from that formula. This is matrix C. For the time being, this is matrix C. And there was another formula in matrix C. Let us make it a little bit harder. If I ask you to give me a function whose derivative is equal to 2x, what is that function whose derivative becomes x squared? It becomes 2x. It is simple. It's x squared. Yes? And of course, not only x squared, but plus any constant. If I ask you what is a function whose derivative is x, not 2x, then what can I do? What is the answer here? A half. X squared, yes. Because when I take the derivative, this 2 will go down and will cancel this half, then I will get x. And if I ask you the same question for x2, give me a function whose derivative is x equal to x to the 2. It is simple to guess. It should be of type x3, x to the 3. But the point is that if I tell x to the 3, 3 goes down. I do not have any 3's here. So this motivates me to divide by a 3 and then constant. So in general, x to the power of a is 1 over a plus 1, x to the power of a plus 1. You see, if it was 1, this number and this number were 2. If this is 2, these numbers are 1 more, 3. And then this is a rough guess that if this is A, this should be A plus 1, A plus 1. So that would be the next formula in my table, which I want to give you some examples today only for this formula. So x to the power of a primitive function becomes 1 over a plus 1, x to the power of a plus 1, and plus c. This is a very, very important formula for primitive functions. Very simple, but very effective. By the way, when I wanted to motivate you, I just give you rational and natural numbers, but there is no need for that. I can now clean it. When I got my conjecture, now I can really prove it for you. I can prove it for you. Why this is a primitive function to this? How should I answer this question? I need to motivate this, that if I take the derivative of this combination, it becomes this. Okay? So let us do that. To prove this, I will take this derivative. Okay? So the derivative of constant is 0. This is a constant. I pull it out. Then a plus 1 goes down. And then it becomes a plus 1 minus 1. But this a plus 1 and the a plus 1 are gone. This minus 1 and 1 are gone. So I am getting x to the power of a. So you see, it doesn't depend on the values of x. But there is a very big exception, which you didn't learn about. It's in Math 3C. We want to learn this year. And can you tell me what is the limitation of this formula?
It doesn't support if a is minus 1.
Exactly. This doesn't support if a is equal to minus 1. Because if a is equal to minus 1, then the denominator vanishes. This doesn't make sense. So it is very, very important. In Math 3C, you didn't need to be careful about this point because they couldn't give you any other questions. They couldn't give you a question which deals with -1 there. But in Math 4, they can. And I want to ask you your question. What happens if it turns out to be -1? So what I'm saying is that what happens if a is equal to -1? So this is vertical line. Let me put it here. I put x equal to -1, and I want you to give me this question mark. This is, you didn't know about this in Math 3C. So this is the only new lesson. Of course, I'm not very surprised because you usually don't memorize the formulas, but what is another name for this? Still, you don't know? What is that function whose derivative is 1 over x? Yeah, please try to memorize this. ln of x, thank you. So 1 over x, so let me write it in two different ways. If you see x to power -1, it means exactly 1 over x. Any of these combinations, the primitive function is ln of x plus a constant. But of course, ln cannot act on negative numbers, so it is crucial here to say that x is positive. I want to write something in blue for you. You don't need to know that, but later you will learn about this. I think I talked about this again. So if I want to write f1 over x, if x is not equal to 0, then you should write ln, but you have to put absolute value of x there. Okay? But this is not mentioned in the book. This is the only one mentioned, but you need to know this only makes sense if x is positive. Okay, I don't want to go further into this table. I want to work on these two today to practice a little bit, refresh your memory, and learn how to use this. But tell me, do you remember, let me just repeat, if I ask you what is the derivative of this, if you go back to the formula sheet or in the book, you see that this is the answer. the derivative of this is 1 over x. So it means that a primitive function for this is ln of x. And this is the only one. I want to stop here today. Try to do a lot of exercises, a reasonable number of exercises for these cases. And so far, I don't know, you might think that, okay, we are just doing guesswork. Yes, more or less we did it. We tried to guess what would be the function whose derivative becomes equal to that. After that guess, of course, we were able to prove it. But it seems that more or less we are guessing than calculating. Yes, it was not the case for derivatives. We were not guessing the derivatives. We were actually doing them. I want to show that this is not the case. If you have this feeling, that's a wrong impression. So, but let me start with first simple questions. So example, determine all primitive functions. Again, do you remember 3 articles? All, a, the. So here, determine all primitive functions for the following functions. I think the preposition should be of, I'm not sure. Determine all primitive functions of the following functions. Let me start with a very simple one, exactly at the E level of Math 3C. F of x is equal to 3x to the power of 5 minus 2x squared plus x minus 1. Let me put plus 1. Let me make this one negative. Okay, I want to find a primitive function for this. So here I have some rules, general rules. I have 1 function, 2, 3, and 4 functions, added or subtracted. Some of them are being multiplied by constants. So those rules, it is not mentioned in the book, but actually you are using it. I just formalized that. So what I want to do this, I would write capital F, meaning a primitive function for this. This tree doesn't affect actually anything because I told you the rule. C goes away, and then I concentrate here. Here is exactly in my table. X to the power of A. The crucial thing is that is A negative 1 or not? That was not your concern in Math 3C, but this is your concern now. Okay, I don't have this problem here because all the exponents are non-negative, so don't worry about this. I only use this formula. For the first one, A is equal to 5. Let me write it once for all. I would write 1 over 5 plus 1, x to the power of 5 plus 1. I really don't want you to write these details. Just do it quickly. But for the first time, let me just do it. Minus 2 multiplied by. What can I do here? Again, that's the same story. It's 2 plus 1, x to the power of 2 plus 1. What is x? The power of x, which is not written, is 1. So this becomes minus 1 over 1 plus 1, x to the power of 1 plus 1. What is a primitive function for 1? It's one special case of the first one. It is x. And then you don't need to put 1c here, 1c here, 1c here, 1c there. It means that, of course, these are different constants, but at the end, if you add them, you can name them one constant. And I have to write this because of this word. And of course, nobody leaves it like that, even though this is finished. Then this becomes 6. It can be simplified. This becomes 2/3. This becomes a half x squared, and then x, and then I have c. So this is what you learned actually in Math 3C, and you were able to solve a lot of it. Now I want to start giving you harder examples, but if you remember my examples when I was teaching you for the first time about derivative, more or less the same ideas and techniques will work here for primitive functions as well. Okay, you might still think that you were able to guess. Okay, yes, this is not hard. You should be able, you were able to guess actually. But let us go to a little bit more nicer problems. So let me not write number 2. Let me increase this little by little. So f of x is equal to x to the power of 2 multiplied by the third root of x. Let us see how it is coming. Nadim, we are finished in 15 minutes.
3 minutes?
15.
No, it's okay, then I can take the other one.
Okay, thank you very much. Okay, so here I want to find a primitive function. I hope that you agree with me. The guesswork is not that easy now for this. Can you guess a function whose derivative becomes this? And then one problem appears by correcting your papers. I realized suddenly people start taking a primitive function for this and a primitive function for this and multiply them. So let me again write it and cross it for, oh, this is not the formula. You are not allowed to do this. Primitive function of f multiplied by g, if you think it is equal to the primitive function of the first one multiplied by the primitive function of the second one, that is wrong. Yeah, please write and cross it over. So do not do them separately. Okay, what can I do now? I want to find a primitive function, and I hope that you are convinced the guesswork is not that easy here. So what should I do exactly? If I ask you to take the derivative of this function, of course you can use the product rule. There is no product rule analogy for primitive functions so far. So, but even in that case, it was easier to use a Mat3C trick, yes? So I would change the form of this function first, because I can only answer primitive functions of the functions that are in my table. So I need to change the form of the function so that I can have a match and then use that formula to answer the question. So I think you can immediately understand what to do. So I can write it as x squared. Instead of the third root, I can write x to the power of 1 over 3. And then I multiply them, it becomes 7 over 3, yes? And now I found the match. The match is again the same formula, but I have to work with fractions. Is this fraction allowed? Yes, because there is only one exception, and that exception is -1. But this is not -1, so I am on the safe side. So primitive function, capital F of x, is equal to 1 over this number plus 1, x to the power of that number plus 1. Okay, and then you calculate, and then you have to remember, you put your c. So here, 7 over 3 plus this is 3 over 10.
Baba,
Yes?
why is it 7 over 3?
I am adding them. Yes? So 2 plus 1 over 3 is 7 over 3. Because a to the power of m times a to power n becomes a to power of. Yes? Okay, so then it becomes x to the power of 10 over 3. So if I add 7 over 3 to 1, it becomes 10 over 3. But here, 10 over 3 is in the denominator, so it will be reversed. It becomes 3 over 10 plus c. I agree that this is not a complicated function, but I hope that you agree with me. Guessing this for this function was not easy from the beginning. So this is a good work. We didn't guess, we calculated something, and we got the answer. If someone asks you, what is this function? You would say that this is a function. It is all possible functions whose derivative is equal to this function. Okay, now let me go to another example. So this is the lesson for today. I want to give you different. This is a very important exercise for the exam actually, so that you know how this simple formula can solve a lot of problems for us. Okay, so let me give you another one. F of x is equal to 5x squared minus 3x plus 2 divided by 3x squared. This is not hard, but let me emphasize on it. If you want to read it in the future near the exam, remember, this is a very nice exercise to make the connection between these things today. Okay? So let us solve this problem. Do you have any guess? Of course, if I want to find a primitive function, I have two generic rules for the sum rule and the multiplication by a constant. And I have some table for the time being in front of me. I will not be able to solve this unless I find a match between this and those and the rules. Can you tell me what I should do first?
We change the form of the function by splitting up the...
Exactly, thank you. Thank you. Splitting up. So here, f of x is equal to 5x squared divided by 3x squared minus 3x divided by 3x squared plus 2 divided by 3x squared. So here, x squared and x squared are gone, so a constant is left for me, 3 over 5. Here, 3 and 3 are gone. In differentiation, I used to bring it up, but here be careful. Of course, you can still bring it up, but I prefer to realize that when I simplify, this becomes exactly my exception. My exception is 1 over x. I myself prefer to keep it as 1 over x, but if you don't want to do that, you can bring it up. But this is the one in the formula sheet. So yeah, you need to get used to it. So here, I simplify this 3 by that 3. I simplify 1x and 1x. That x is left in the denominator for me. But here, no cancellation is possible. But this is not in the right form. So I use the same trick. I bring x squared up. So it becomes 2/3 x to the power of negative 2. If it was not here, it was a Math 3C problem again. But now it is here. This is the only thing that you learned this year. Okay, now everything is ready for me. Because 3 over 5 is a constant, that is the first row. And then 1 over x is this formula, that is ln of x. And x to the power of minus 2 is this formula, because a is minus 2 and it is not equal to minus 1. So everything is settled down. So I can now start to differentiate. Sorry, to find the primitive function. A primitive function for a constant is that constant according to the first row on the table, but multiplied by x. A primitive function for 1 over x, it's in the table, ln of x. And 2/3, I can pull it out. You need to be patient, Elliot. So x to the power of minus 2, what should I do? I need to write 1 divided by minus 2 plus 1, which is minus 1. And then x to the power of minus 2 plus 1, which is again minus 1. And then I have a constant at the end because I have to give all the answers. I prefer to simplify a bit. So this becomes 3 over 5x minus ln of x. And then I have minus 2/3. This is minus 1. X to power minus 1, I prefer to bring it back to make it positive x. And then constant c. So I hope that again, it was probably far away from your imagination that this these are the only functions whose derivative becomes this fraction. Okay? It was out of reach to guess. So it means that what we are presenting is not just based on pure guesswork. It was not easy to guess this answer for this. So if you have, for example, a computer, you can just put this function and ask the calculator or your program to differentiate this. Yes, and then you simplify it, you see that this would be the answer. So this is a simple exercise, but it includes everything that I wanted to talk about that with you. Okay, I will continue a little bit about this.
Mr. Babak,
Yes?
when we were creating the table for the derivatives,
Yes?
then we had this limit formula.
Yes.
Is there any way to fill in the table using a similar formula for primitive functions?
No. Because primitive functions are
So that's the
defined.
guess part.
No, you have to do the guess part, yes. This part is the guess part. Of course, these are not hard to guess because these are standard functions. So if I just, the guesswork is only happening with these coefficients. That is not, I would say, a crucial guesswork. But yes, that is not the same. The notion of limit comes in when you want to talk about the definite integrals, calculating areas, volumes, and things like that, okay? But this, for the time being, there is no connection between these ideas. It was the ingenious of Newton who recognized that there is a relation between antiderivative or primitive function and the notion of the area under a curve. Okay? We come back to that later, but let us just focus here. So you need to know how to define primitive functions by matching the functions with your table. Okay, so let me give you some examples. For example, number 4, I can do this number 4 and then we can finalize. I will not move on. Next time I will provide you with more examples. This integral part is actually very crucial. It's really worthy to pay a lot of attention if you want to go to a technical university. It's always with you. Okay, so what do you think if I want to find the primitive function for this? X to the power, let me write, f of x is equal to x to the power of, let me write, the third root of x squared multiplied by x minus 1 to the power of 2. We want to find a all primitive functions for this function. And again, hopefully you agree with me, it's not easy at all to guess. We can wait until the end. So you see, it was not easy to guess this function for this function. Yes? So let us now go there. Do you have any suggestions? How should I start with? What I should start with?
To begin with, you can rewrite the third root of x squared as
Yes, and then?
x squared to x to the power.
No worries, I can do that then. So you are saying that I want to write this.
Then we expand x minus 1 using.
Exactly. So we do this and we also expand this. It becomes x squared minus 2x plus 1. And then, of course, it is clear for you that I can multiply it. So then it becomes x to the power. Let us do it in my head. 2/3 plus 2 is how much? Is 8/3. And then I have minus 2. 1 plus that 1 is 5/3. X to the power of 5/3. And then finally, I have x to the power of 2/3. So that is not a big deal. Now you understand what to do, yes? Because all of them are following this formula, okay? And I think you can do it yourself. I just write it and I can do it quickly. I'm just using this formula, okay? So this becomes 3/11, x to the power of 11/3. And then this becomes x to the power of 8/3 3 over 8, so it becomes 3 over 4, and then finally you get 5 over 3 and 3 over 5, and then a constant. So if you do it patiently, you will get that combination. Hopefully, if I haven't made any mistakes. Yeah, please do it at home so that you can confirm that this is indeed the answer. And I hope that you agree with me again, it is not possible easily to guess this or that function. So it means that we are indeed doing something. We are not just guessing. Okay, thank you very much and have a nice weekend. So I will end here. I will be in Zoom if you have any questions. Otherwise, we will go.